Welcome to the 1015 podcast. This is Philip Schlump. So the question is, why test code? And it's also partially how to test code. I mean, if you're in the software field, you could actually be a professional in doing quality assurance and just do testing. That's one possibility out there, but why test software? Let me tell you a couple stories. This one is, a little earthy, but, we're in Wyoming. They have ranchers here, and they have earthy things happen on ranches with cows, and I've been involved in some of those. This is not a cow story, however. I was driving across Shirley Basin some years ago at excessive speed because it's a long ways across Shirley Basin, and also there's only one rest area, and I really, really needed to go to the rest area. So, it's way out there in the middle of nowhere, literally. I mean, there just isn't anything out there by this rest area. And when they rebuilt the rest area, they made some nice choices. It's heated by passive solar heat, so it's got these big windows at the top, the skylights, that let in the sunshine to keep it warm, and these big, thick walls to absorb the heat. And in the summertime, it's got louvers that can close so it doesn't get like roasting hot in there. And this was a summer day. There was puff balls going overhead. Just one of those beautiful clear days with little puff balls. And this being Wyoming, the puff balls were in super speed mode, going about 60 miles an hour across the sky, just zooming across. Idyllic day. And I pull into the rest area. And there's one other vehicle in the rest area. It's a Wyoming Department of Transportation truck. And I really need to go, but, sometimes you see something that's odd enough as I pulled in, parked, shut off the car, hopped out, that even in my state of urgency, I noticed that, yes, the truck is sitting there running with the driver's side door open and nobody in it. But I needed to go, so I ran into the restroom. And I go in, and there's one person in the restroom. Fortunately, the other stall is open, and I dash for the other stall and sit down. Now, at about this time, this is an urgency, so you know what's happening as you're sitting there. And one of those puff balls manages to go over, and it goes from light to dark. Okay? And the person next to me in the other stall says, "Oh, man, it's about to happen." And then it goes from dark to light, because remember there's those big skylights? And at the moment that it goes from dark to light in that room, a magical thing happens. You see, they had observed that people tended to leave the faucets on and not flush the toilets, so they'd put in automatic toilets and automatic shutoffs on all the sinks. And now these things all use photo sensors. And at the moment when the whole interior changes in light, everything flushed and every sink kicked on for about 3 seconds, all at the same time. Now, those of you that have had some civil engineering background know that you are not supposed to flush all toilets all at once. And yes, you could hear the ones in the women's restroom all flush all at the same time. And I was sitting on one. And then the next thing you never really want to hear while you're sitting on the toilet is the person next to you say, "Well, did it get you? I can get your roll of paper towels if you need it." And the water level is rising, not going down. And it's rising and not going down. And certain parts of the human anatomy, at least for a guy, well, let's not go there. In any case, let's talk about the testing side of this. These little faucets and everything had computers on it that used photosensors, and the photosensors were no doubt tested in the lab. And in the lab, they have fluorescent lights like most bathrooms. They don't have skylights overhead with 60-mile-an-hour puff balls cruising overhead, changing the lighting multiple times a day. And so the guy next to me in the stall says, "Yeah, they put in those things to cut down on the water consumption so we wouldn't have to pump out the septic so often. Now that they got those in, I'm pumping it out every week. Man, it's a disaster. We got to get those things changed out. But man, they're just flushing every time a cloud goes over." And about this time, it's gone dark, and I'm thinking to myself, the situation is now critical. because if it goes any higher, it's a bad situation. And then it goes from dark to light. 60-mile-an-hour puffballs move fast. So, testing, no matter how good your plans are, has to meet the real world. I've got a couple more examples of that. I worked on a grocery store system. And part of the grocery store system was scales that weighed the vegetables. And we had this installed in Riverton. And in Riverton, it was working except for one aisle in the grocery store. That, sometimes it would work and sometimes it would fail. And I had worked on this software in the lab and tested and tested and tested. And I could not reproduce whatever the failure was that was happening out there in the field. And finally, I packed up a suitcase, drove to Riverton, Wyoming, got a hotel room, and went to the grocery store and got trained to be a bag boy. And they ran that aisle. And the first day, it worked. And the second day, it worked. And on the third day, man, I'm thinking this is winter and this is a lousy day to be here. It is snowing outside, the wind is blowing, and this aisle is right behind the doors, and every time somebody opens the door, you get this blast of cold and snow inside. And it's just not pleasant. And I'm bagging all day long. And I'm not getting paid to be a bagger here. Okay, I'm here to observe what goes on and why it fails. And then she goes to scan a head of lettuce. Nice lady working at the cash register. I remember her clearly. She scans it, and the front door opens. And suddenly, right there, it failed. And I'm thinking to myself, look, the scale has an error code on it. We've never noticed the error code. And consequently, we help the people move to a different line, and now I'm working on the error code. And I look it up in the manual, and it isn't listed. And I'm going, damn, that's kind of the manufacturer. So I called him on the phone, and I'm talking to him, and finally they transferred me to the development group, which they'd never done before. And this is a pretty good-sized company that does scales. And I get one of the engineers, and I tell him I get this error code, and I read off the number. And he says to me, in the most clear tone, you can't get that error code. You'd have to cool the scale by like 40 degrees in 15 seconds. And I'm thinking to myself, yeah, in Wyoming, you can be inside a building and cool a scale 40 degrees in 15 seconds. In the middle of a snowstorm, if the door opens and it goes from room temperature to below freezing. In any case, both of these things involve a common theme in testing software, and that's assumptions. Break down the word, make an ass out of you and me, and, assumptions are the big thing. If your assumptions about your testing are wrong, then your testing is going to produce unexpected results when it gets out in the field. And this happens more frequently than we would like to admit. Things in the real world are complicated and ugly and dirty and messy, and lots of software these days. Software is eating the world, is out there in the real world. So even if you do good quality testing, you can still have problems. Now, here at the University of Wyoming, we have a lot of formal verification of software where they mathematically prove it's correct, and that is good up to the point of, did they actually start out with the right assumptions in the requirements? Is it matching with the real world? And you can formally specify things, and some stuff you can eliminate, like that second case in the grocery store. Well, one of those things that automated testing should have, and formal testing definitely would have shown, is that, yes, you have an error code that you're producing. It should be in the manual. It should be something that you can check for, not we left an error code out. And that's actually a big cause of defects in software, is leaving things out. So that kind of stuff can be prevented. Now, the second kind, no matter how much you build your system, the world is a complicated place, and you've got to meet the real world. You have to go out there and actually do things. So, short of actually sending your software out into the world and testing it with real customers and seeing what they do, which is what we call a beta test group, it is very, very difficult to test every use case. Unless your software is some very small specific thing. It's very hard. So there is that aspect of testing. Now, how important is testing? I was reading the other day that there was a cryptocurrency that its price, and within a few days, the valuation of the company had soared to $523 million. Before, yes, somebody discovered that somewhere in the software they'd left out a single division on one line. And oops, guess what? They shut down the entire cryptocurrency and their valuation is gone. Because guess what? That division was important. So a single line error destroyed $500 million worth of value in one day. And those kind of things can happen. I think you're going to find that's going to happen more and more in this world. There was a high-speed trader that provided services to people like E-Trade and Scottrade on the NASDAQ market. And they deployed new software that interacted badly with the fact that they had failed to undeploy some other software that was old software that was supposed to be removed, but it didn't get removed on all the computers. And they lost $400 million in an hour by buying the wrong things. So these things are critical and disastrous. Let alone we look at somebody like Boeing, who failed to properly test their software for their MCAS system on their 737 MAX. And although it is probably not going to destroy the company, they have lost their market share and destroyed their reputation for one of their airplanes. A multi-billion-dollar mistake that may actually wipe Boeing out for failing to test some software. So software testing is valuable. It's important. And the other question that we should talk about is how you go about doing it. Because, there's testing. You run it once, which is the way most students tend to do their testing. And it looks like it might work, so you turn in the homework. And that is not the way a software engineer tests stuff. We want to look at all the possible different cases, or at least good representative examples of each possible case. Figure out what the correct answer is. We want to build a piece of code that says, okay, I'm going to run this piece of code with a set of input. And whatever the process is that piece of code is, I know what I'm supposed to get as output, and then I'm going to check to see if I actually got that output. And if I didn't, then I'm going to report an error in my testing. And I'm going to go through a series of tests that do this over and over for each of the different cases in the software. And when I get pieces built that match all of my test cases, then I'm going to ask some questions like, did I leave out any test cases? Is it complete? Have I made my test cases clear? Because the reality of software is it's not just what you build today. It's how you're going to change it 6 months, a year, 2 years from now. And you may be looking at it and going, well, this is just a homework assignment. But I'm still running software that I wrote 20 years ago and still maintaining it. And I use this stuff over and over and over. And consequently, it has to have not just test cases, but yes, some documentation and some instructions on how to build it, how to fix it, what it does, what its options are. And that's just stuff that I've written for myself sometimes. But in amidst all those things, it has to have a set of tests. So that later, 2 years from now, 5 years from now, or when somebody else comes along with the same software, they can look at it and say, well, it doesn't work in this case. Is it in the test? They left that test out. Let's add another test to it. Let's go back and look at it and say, okay, now we've got a test. How do we fix it? How do we know that the fix that we added didn't break something else that it does? That's a really critical piece. And when you build all of these tests together and you test it and you build a system for testing, generally speaking, you're going to find that test code is quite often larger than the actual code itself. If you look at, I don't have access to the source code to all of Python, and it is public source. You could go look at it. But I'm familiar with the source libraries for Go. It's a different programming language. But you look at the source code for Go, and 2/3 of the libraries for the Go language are the test cases. There's more code involved in building the tests than there is in the actual library. And there is just as much code involved in all the documentation for the library as there is building the tests. So those are the other pieces that get involved in the process of engineering. So you can plan, you can build the code. Now you got to test and verify the code, and you've got to document the code. And a project isn't done until it has all of its pieces completed. So that's kind of the why to test, and a little bit about how we're going to go about testing. And yes, as a part of your homework in this class, testing is required. But you're going to find something interesting when you test. And this may not be true so much in this class, although later in the class it will be, as we build bigger things, is that testing allows you to get to a finished product faster. And I know that seems odd because you're going to have to add all of these tests. But if I've got this piece, think of the size of a sheet of paper, and I can take half of it and I can test it and verify it. And then I can take a quarter and I can test that and verify it. And then I finally get to the final program, and it has to have some other things to test and verify it. But now 3/4 of it, I know it works. And I'm pretty confident that those pieces that I built are done. And then when I go to test that last quarter, I can go, okay, this last piece that puts it all together. Yeah, I'm still testing it, but I can trust the pieces that I've built. And I don't have to wonder when I have something go wrong, well, is it in that first half that I worked on, or is it up there? And although your tests may not be perfect, even moderately good tests at that level will save you lots of time in hunting things down. The reason it saves you time is really this. And I want to go back in history to Grace Hopper, who invented COBOL, which was pretty much the world's first programming language. Fortran is the other one. Those are languages that I learned when I went to school in the Dark Ages. And one day she was working on a computer and it wasn't working right. And she went to investigate, and eventually she got out some tweezers. And this is a computer built with thousands of tubes. You don't see tubes anymore except for some very specialized things. Everything is transistors. But these were actual tubes, vacuum tubes. And she went and looked in the computer, and yes, a moth had flown into the computer and died in the circuit. And that moth was disrupting the behavior of the computer. And she pulled the moth out, and later when she was asked by her boss as to what she had been doing, she explained that she had debugged the computer. And that term has stuck with us. Much to Dijkstra's chagrin, he wants us to call them all defects, but most people call it debugging your software, which is for pulling the moths out. So that's my little anecdotal story about why we call it debugging. Debugging is really defect removal quite often, or failure to meet the requirements for a program, or just not doing the right thing. But yes, get out your tweezers. I actually have a microscope in my lab that I occasionally use with hardware. Get out the microscope and find the little bugs and pull the bugs out. All right, we'll catch you later.